G'day guys, and welcome to our video on modulation. Modulation refers to the transformation of an electrical signal into another medium, say light. And there are three reasons why you might want to change an electrical signal into a light signal. Number one is, say I have a source here and a receiver here, and I'm trying to transmit my electrical signal via wires. That means I'm changing the voltage at the source here. So the voltage over time might look something like this, and that is giving information to the receiver. If the voltage is changing over time, unfortunately if these wires are really long, they also have resistance. I'll give them resistance R. And if there is resistance in the wires, then the power loss over the wires is given by the current squared multiplied by R. And that's a bit unfortunate because it means I'm wasting power. Power that could be used, picked up by the receiver is being lost as heat in the wires. The second reason is that if you try to send an electrical signal a long way over a wire, you get what they call attenuation. So I'll list these reasons down. 1, power loss, and 2, attenuation. Attenuation just means the signal gets distorted. So if you might have a very clear voltage over time signal at the source, but by the time it gets to the receiver, it may not have that same shape. Could look a little like that. The longer the wire is, the more attenuation you get. Light signals do not experience the same degree of attenuation as electrical signals. And the third reason you might not want to transmit your signal through wires is that there is a frequency limit. So imagine Morse code for a second. Morse code is made up of dots and dashes, or dits and dars, and it basically requires someone to be tapping on the Morse code tapper to complete the circuit at the source, and those signals go to the receiver. Now a very good Morse code signaler could tap that thing back and forward very quickly, creating a lot of dits and dars, dots and dashes per second. And the receiver would be getting a lot of information very quickly. This is known as bandwidth. So the higher the frequency this person could make those taps, the higher the bandwidth. Unfortunately, in a metal wire, there's a frequency limit. Once you get up past 100 megahertz, so 100 times 10 to the 6 dots or dashes per second, you start to lose information very quickly. However, if you're working with a fiber optic cable, so working with a light signal, you can get up to 10 to the 12 dots or dashes per second before you have a loss of information. So you would modulate an electrical signal into light because there's a higher frequency limit with fiber optics than metal. So let's talk about for a second how you'd actually modulate your signal. First of all, we'd take away these wires here, and we'd replace them with a fiber optic cable. I'll draw that especially large there. And this is just a cable for the light to bounce through on the way to the receiver. Secondly, we need some light source at this end, at the source end. So the source is some kind of AC signal, perhaps. And we'd use an LED here. So I'll try and draw that. There's our LED. So as the light source shines through this, as the voltage shines through this LED here, we'd get varying intensities of light bouncing down that fiber optic towards the receiver. And on the receiving end, we'd have something like a photodiode or a light-dependent resistor, something that will recognize when there's a high intensity of light and a low intensity of light. So we actually understand the signal coming through. This end is the modulating end, because that's when the electrical signal becomes a light signal, so that's the modulating end. And over here it's not modulating because the light signal is becoming an electrical signal. This is known as demodulating. Let's look at how different voltage electrical signals become light intensity patterns. So first of all, a very simple voltage pattern with a voltage always positive, voltage over time, and then next to it I'll do another graph, and this would be the light intensity over time, intensity. And we will not be looking at carrier waves in this example here. This is just plain intensity of the voltage. So if this is the voltage graph over time, as the voltage becomes greater, we expect more intensity through that photodiode, more intensity through that LED. So we expect higher light intensity over here. So zero light intensity where it's zero voltage, and then high light intensity at high voltage. That's one example. It's just when the light intensity signal is the same shape as the voltage. Let's look at a more complicated example, and I'll introduce this concept of a carrier wave. So say I had a voltage signal, and it looked roughly like this. Voltage, time, starts at 0, jumps up, then back down. It's got a negative voltage now, comes back up even higher, and then down to 0. There's such thing as a carrier wave, which we can use when we modulate. And the carrier wave says basically we're going to combine this signal here with this wave here. This is the carrier wave. And we'll make it very small frequency. And I'll show you how that works. First of all, let's say that we've set up the system so that when we get this minimum voltage here, we get 0 light intensity. So the light intensity will run along that axis there, intensity over time. And when we get max voltage there, that's when we have the maximum light intensity. That means that when we have 0 voltage, we have some degree of intensity there. So we start out and we're already making that wave there. And then we get to this point here and there's an increase in voltage. So our wave actually gets bigger like that. And then we're decreasing, and then at this point here we're back down to 0 voltage. And then since now we're dealing with a negative voltage, gets even smaller, all the way down to this point here where we set at 0 light intensity, and then back up, and then moving this out of the way, we have our largest peak yet. So now we're at that point there, keep going up, and then back down to 0. And notice if I fill in a line over all these little peaks here, I get the same shape as this signal here. So what would be bouncing through this fiber optic cable is this varying light signal here, and when it gets to the receiver, hopefully there'd be something in there that turns it back into this shape here and fills in the appropriate voltage to whatever is receiving over here, say some kind of speaker. The one thing I'm going to leave you on is don't confuse this wave here, if you've looked at the photonics videos on light, with the actual frequency of the photon. This is still a varying intensity signal. It's not the actual frequency of the photon, which we'd find using Planck's constant. So to summarize this lesson, the three reasons you'd try to use a modulated signal and not just electricity is because power loss occurs over large distances. You get a scrambling of your signal with electricity, and there's a lesser degree of that happening with light. And there's also a frequency limit when it comes to wires and electricity. Whereas with fiber optics, the frequency limit is a lot higher, so you can have high-speed internet in which you can actually watch a YouTube video without waiting for it to load. With modulation, there's a modulating part and a demodulating part. the light intensity is supposed to bear a resemblance to the voltage, and if you're using a carrier wave, it's basically a bunch of peaks that describe the shape of your voltage graph over here.